Welcome, viewers. Today we have a topic before us, and the topic is shear stress and punching shear stress on foundation footing. In our last video, we talked about footing, how to size a footing, and using the bearing capacity formulas to size a footing. But today we want to look at how we can be able to design the footing by checking for the shearing stress on the footing as well as the punching shear stress on the footing. Now, for us to do that, we have a rectangular footing on the board, which I call LS and LY as the dimensions of the footing. And we have an area which we call the critical perimeter for punching. Now, according to our code, the critical perimeter for punching is measured from the point 1.5 H from the face of our column. So if this is our column, if this represents our column, our punching is measured from this point, which is 1.5 H from the surface of the column, where H represents our thickness of footing. Now, in this case, we do not know what H stands for, but we know that H represents our thickness of footing. Now, let's look at how we can obtain the punching shear stress for this particular footing. Now, looking at the board carefully, you can see that the area of failure of this concrete footing is outside this perimeter, this shape, which have what we call the critical perimeter. So the area of failure is around this zone, This is at the point of failure. So you can see the cracks developing at this point. These are the area of failure. So the punching shear failure will occur around this zone. So we need to obtain the punching shear stress in this area. Now, for us to get that, looking at the shape we have on the board, we have the size of the footing, AX and AY. Now, like what I've done, this is a curved part of it. In this curved part of it, we have it at the 4 sides. Now, remember that we said that the critical perimeter is measured from the face of the column, which is from this point to this point, gives us our critical perimeters. The same thing happens from here down to this point. It's the same 1.5 H. So you can put it 1.5 H. Similarly to here 1.5 H, here to here 1.5 H, here to here 1.5 H. So all those measurements are taken from the face of the column. Now, what we want to do, we want to calculate the punching shear stress outside this area. Now, I said we are going to take each of these shapes one after the other. If you look at these particular shapes, it represents a sector of a circle. Similarly, here represents a sector of a circle. So I'm just going to draw it straight off so that it looks like this. So I've labeled this sector. I call this sector 1, sector 2, sector 3, and sector 4. So we have 4 sectors of this particular shape. Now, let's start with the perimeter. All right? Because for us to get, we need to know what this perimeter is. We call it the critical perimeter. So for us to do that, I'm going to calculate first of all this one. Remember that the perimeter of a shape is the length. So we're calculating this one, and this one. So let's do these ones first. I said perimeter of the sector of the circle. We have perimeter of sector to be theta over 360 times 2 pi r. So if we solve this is at 90 degrees. So we're going to have this expression to become pi r over d. Now that is for one of these sectors. Now you can see from the board we have 4 sectors, 1, 2, 3, 4. So we are going to multiply it to get the total perimeter. So if we multiply pi r over 2, we're going to have 2 pi r. This is for the first sector. All right. So multiply this by 4, we're going to have 2 pi r. All right. So that gives us the perimeter of the first sector, where arrow in this r represents the radius. Remember that if we take this one, it means also that the radius here becomes 1.5 H, 1.5 H, 1.5 H. So we're now going to substitute for our radius, which is 1.5 H. So if we solve, we say that the perimeter of the sector 1 to 4, the total perimeter of sector 1 to 4 becomes 2 times pi times arrow, where arrow represents our 1.5 h. So if we do that, we are going to have this thing to be 3 pi h. Okay, so we'll have it to be 3 pi h. To be 3 pi h. So having gotten the perimeter of the sector, it becomes easy to obtain the total perimeter of the entire shape, which represent the critical perimeter. So we can therefore say that our critical perimeter, P critical, let's put it this way. Remember, we have here, we know what from here to here is. Remember, AS represents the sizes of AS and AY represented the sizes of our rectangular columns. So this is for the column AS. So we can repeat it. So here will also be AX2. So we can just add this, add this, add this, and add this. So um, it becomes our 4AS. So while this and this are the same, we have AY on this horizontal axis to be the same. So here and here is AX, we have AX here. On this direction, we have AY, and we have AY. So let's add them up. So we'll have 2AS plus 2AY. All right. So that gives us that for the square shape, plus we have 3 pi h. So the total critical perimeter, P critical, becomes 2 brackets AX plus AY plus brackets plus 3 pi h. All right, so this gives us the total perimeter of this shape. So we have gotten the critical perimeter for it. The next thing we want to get is the value of the shear stress that are acting outside this critical perimeter, which is this position. So we're going to look for the shear stress acting outside this critical perimeter. So let's go on and work on that. We need to obtain the area outside this critical perimeter. For us to do that, let's first of all obtain the area inside the critical perimeter. So when we subtract the shape of the entire footing from the area inside the critical perimeter, we'll have the area outside the critical perimeter. So let's go ahead and work on that. Perimeters, we're going to calculate the area within the critical perimeter. So solving from where we stop, having got to the critical perimeter, we need the area inside the critical perimeter. Now the area inside the critical perimeter, like we have seen, are the areas where we have the crack. So we are going to solve for that area inside the critical perimeter. Sorry, the area inside the critical perimeter are these areas where we have the crack. So we want to calculate the area inside the critical perimeter. So once we calculate the area inside the critical perimeter, we are going to minus that area from the total area of the footing to get the area outside the critical perimeter. All right, so let's solve that and get the formula for calculating that. Let's take each of the quadrant of the circle. We'll have the shape as this, have it as this. One of the shape will have it as this. All right, now like I said, the distance from this is the face of the column, so we said that that distance is 5h. We have here also to be 1.5h, sorry, 1.5h. So what we need to do, let's calculate the entire area of this sector. We have done that before. Maybe we've not done that. We'll calculate the entire area of the sector of the circle. So this is the sector of a circle. We're going to calculate that area. Let's call this sector 1. So let's calculate the area of this sector. Remember that area of a sector area of sector 1 becomes theta over 360 times pi arrow square. All right. Now, in solving this problem, we have a theta to subtend an angle of 90 degrees. So it becomes 90 over 360 times pi arrow square. So working this out, we have this to become 1 over 4 times pi. Arrow becomes a 1.5h. All right, a 1.5h squared. So this gives us the area of one of this sector. Now remember, we are interested in the entire area. So let's assume that we have this thing to be, the shape of a rectangle. Of course, we can get the area of this shaded part by saying area of shaded part becomes total area of this small square, which is 1.5h times 1.5h minus area of the sector, which we've just gotten to be pi 1.5h square over what? Over 4. So this gives us the area of the shaded parts. Now remember, in that sector, we have 4 of such sector. We have 1, 2, 3, 4, and we have just dealt with 1. So what I want to do, we are going to pick this as a square. Take it this way. We take it this way. We take it this way. All right. So once we get the area of the entire square, we're going to minus the area of this shaded parts. We're going to minus the area of this shaded part. Once we minus the area of this shaded part, whatever is left becomes the area of this shape. So we minus the area of this shaded part, which we have just solved for. So remember that the area of this shaded part, we have 4 of the shaded part, which is 1, 2, 3, 4. So the area we just got in is going to be multiplied by 4. Total area of shaded part becomes equal to 4 brackets 1.5h square minus pi over 4 r square. So multiplying this, we are going to have 4 bracket 1.5h square pi 1.5h square. So this becomes the total area of the shaded portion of this particular area. We have 4 of it, which we have done. So we have the total area to become this. Now this total area, we are going to minus it from the total area of this particular square we've just gotten. Now, if we want to do that, let's take a look at it again. We can obtain the length of this shape from here to here using this one as a guide. Remember that from here down is 1.5h. From here down is AY. From here down is 1.5h. So we have 1.5h, AY, and 1.5h as the total length on this side. So the same thing we are going to have on this direction, 1.5h, 1.5h, and AX. So let's do that to get the total length and multiply the area. I've not calculated the area of the shaded portion. We have the 4 shaded portion. We are going to calculate the area of that square. So we have that area to be area of square portion becomes, we have the length to be length times breadth, which is equal to, for square footing, it will be length times length. Okay? So now let's start with the length, Lx. Lx becomes, our Lx, sorry, let's not use the subscript. Let's start with the length, L1. So let's call it L1. L1 becomes 1.5h plus 1.5h plus AY. All right. So if we work this out, we'll have L1 to become 3h plus AY. Similarly, we'll have B to become the same thing. This time we're going to have AS becomes 3h plus AX. That is for the horizontal direction. So if we have these two, it means the area becomes AY plus 3h bracket AX plus 3h brackets. So this gives us the total area of the rectangle or triangle, whichever case it is that you are solving for. So, but let's assume it's a rectangle. So if you solve that, you have the area of that shape. Now the area of that shape minus the area of our shaded portion, which is this. Remember, we have 4 of this in that our punchy shear shape. So I've gotten their area to be this. So we are removing them from the entire area so that we can have the area that is, we can have the area that is within the critical perimeter. So for us to get the area that is within the critical perimeter, we'll say area within perimeter becomes AX plus 3h bracket AX plus, sorry, AY plus 3h, AS plus 3h, have this minus, we'll have the whole of this 4 bracket 1.5h square minus pi 1.5h square. So that gives us the area inside the critical perimeter. So that area becomes AS plus 3h bracket AS plus 3h minus 4 1.5h minus pi the 1.5h. Okay, so we can simplify that further. If we do the simplification, we can call that area outside the critical perimeter to be AX plus 3h bracket AY plus 3h minus, let's factorize out, we have 1.5h square, h square, 1.5h square brackets, we have 4 minus pi. Simplify it, the area within the critical perimeter, so this gives us, let's call it area W. It becomes the area within the critical perimeter. We'll simplify it further. So that gives us the area inside the critical perimeter. All right, so having gotten the area inside the critical perimeter, we now need to obtain the area outside the critical perimeter. Remember that the Sponson shear is checked for the area outside that critical perimeter, and that is why we need to get this. So let's solve for that as we solve for the area outside the critical perimeter. All we need to do for that is to say that the area of the entire footing minus the area within the critical perimeter. So let's do that as we obtain. So to calculate the area within the critical perimeter, which we have just gotten, we need to obtain the area outside the critical perimeter. So area outside critical perimeter is equal to area of the entire footing, which is Lx times Ly, minus the area within the critical perimeter, which is the whole of this down this way. That is the area within the critical perimeter, which we've gotten before. And we'll have the expression to be minus, we'll have AX plus 3H, AY plus 3H, and I'll have it as minus 1.5H all square minus 4 minus pi. All right, so this is the expression for the area outside the critical perimeter, where this expression represents the area within the critical perimeter, which we derived from the beginning. So this is the area outside the critical perimeter. Now, the punching shear, like I said, the punching shear is checked for the area outside the critical perimeter. Now, what we must understand is that in practical analysis of this, the axial load that is acting on this footing it varies across the surface of the footing. All right. So the stress at the point of application of the footing is expected to be greater. Is expected to be greater than every other section of the footing. But assume that the stress due to this axial load from column is acting uniformly on the entire footing. But in real life, it is not acting uniformly. But that is the assumption. That's why when you carry out a finite element analysis of this, you discover that the stress is concentrated at the point of application of the load. But we're assuming the stress to be uniform all over. So we know that the axial stress on this footing is uniform. So what we need to do is to say the axial stress of the footing divided by the area of the footing. Okay, so the axial stress from column, axial load from column, divided by the entire area the load is acting. And it's assumed that the load is acting on the entire surface of the footing. So that is the assumption. So we are going to work by that assumption. So it means that when we have a service load for a column, let's write this way so that we can keep referring to what we are doing. So if we have a service load N, service load of column, it means that the stress that will be acting on this footing becomes uniform stress. Let's call it uniform stress on footing becomes the load over the area that the footing load is, the axial load is acting, which is the area of the footing. So that area will have it as Lx times Ly. All right. So that is the area, that is the stress on the entire footing. Now, when the stress is acting on the entire footing, it represents the maximum stress. But we know that as the stress acts uniformly at this point, the stress will differ. The stress, as we solve this one, we're going to have it in kilonewton per meter squared. All right. So if we have this pressure on the entire footing, what will be the pressure acting on the outside of this press on the footing due to this service load become the axial load from the column, which is the service load, divided by the cross-sectional, the surface area of the footing, which is expressed in kilonewton per meter. Now, in this case, what we want to check, which is our punching shear stress, is not the entire the stress on the entire, this is a punching shear, this area that is outside the critical perimeter. So for us to get that stress of the area outside the critical perimeter is to say that stress acting on that area of the footing. So now for us to get the load, the equivalent axial load that is being exerted outside the footing, is to say that this uniform pressure, can say load on critical area, which is equal to area outside the critical perimeter. So we'll look at the critical area for punching, which is the area outside the critical perimeter. So we need to look for the equivalent load that will be acting. If we have n kilonewton as axial load acting on the entire surface, now what will be the equivalent load acting on that particular area? The equivalent load acting on that particular area will just be that area multiplied by our stress in kilonewton. So that will be load. So load on critical area, let's call that load NC. So we can say that NC becomes N over LS times LY times the critical. All right, so we look at the area outside the critical perimeter. So that area is the area we're interested. So we are saying that the total stress acting on the entire footing is N over Ls times Ly in kilonewton per meter square. So if that is the total stress acting on this footing, we needed to have the stress, which is represent our punching stress, that is acting outside the critical perimeter. So we need the area of the critical perimeter, which we have gotten as, we call that our A0, which means area outside critical perimeter. So we are going to multiply that area by our stress, which is acting on the entire footing. So if we do that, we can have the load that is acting outside the critical perimeter. So if we do that, we'll say this stress becomes the stress acting on the critical, acting on the entire footing. So we can now say that this stress times the load, this stress times the area, sorry, this stress times the area outside the critical perimeter will give us the load outside the critical perimeter. This one is measured in kilonewton. So this becomes a load outside the critical perimeter. We'll call that load N1. So what we are saying, now we got to the load outside the critical perimeter, which we need to calculate our punching shear. We are saying that punching shear stress becomes the load outside the critical perimeter divided by the effective depth D, all right, multiplied by the critical perimeter itself, okay? So that gives us the punching shear stress. So having gotten the punching shear stress, we need to check with our code the maximum allowable shear stress. You check from your code. If you check from your code, you can check if this punching shear stress is lesser than the maximum allowable shear stress. Now, according to BS 8110, and we'll have that shear stress to be, for the section to be 0.8 FCU, square root of 0.8 FCU, or we say 5 Newton per millimeter squared. So whichever is lesser. So it is expected that our punching shear stress should, which is this, our punching shear stress should be lesser than any of these, the lesser of any of these, either 0.8, the square root of FCU, where FCU represent the characteristics strength of strength of concrete, and we have that. So this is how you check for your shear, punching shear check for your foundation. And so you have, all right, so once you have done your check for punching and your punching shear stress is less than the action is okay in terms of punching shear stress, But in a case where you have your applied stress greater than the maximum allowable punching stress, which we have mentioned, about V 0.8 FCU and 5 Newton, what you need to do is to increase the depth of the section. So if you have the thickness of your footing to be, for example, 200, and you check for this and you discover that it fails punching shear check, all you need to do is to increase the thickness and retry it again, and you will be able to have the required depth of. All right, so the formula B is greater than column size plus 3H can be used as a check in your preliminary design. You can take a tentative H using that criteria. From there, you can go on and do your code check. So I believe you do enjoy the lecture. So if you find the lecture interesting, do well to subscribe to our channel. I hope to see you in our next class. Have a wonderful day. My name remains Engineer Vaga. I remain your humble host. Thank you.